Hey, good afternoon, everyone. Let's see how many people are here. Hey, not many people. Good afternoon, everyone. Let's see all the highs in the chat boxes. Okay, I can see Aditya and Chaitanya and Pranay and Vedant. Okay, yeah. So, are other people joining in? I hope they are. Hi, Anushka. Hi, Priyanshi. Okay, yeah. Good afternoon. So yeah, I went through some of the answer scripts yesterday, and it was fine. Mostly the class did pretty well. I think the highest mark was 8 or 9, 9 I think. Till I have not checked all of the papers, but till the ones that I have checked. Okay. Okay. Yeah. So today we are going to discuss about plastics, and this is like the additional topic. We have covered most of all. We've covered the core topics in the syllabus, but there were two things that we thought of covering in in this part of the course. So we thought of doing two things. One is plastics. One is a basic discussion on plastics manufacturing. We'll not go in too much detail. There is a separate course on plastics and composites on which is, I think, the next semester for you guys. So if you guys are interested in the topic, then you can take up that course. I'm not sure whether it is next semester or next semester. One of those semesters. Okay. So yeah. So that course is going to detail out the whole, uh, you know, untangle the web of plastics basically. Uh, but in this class, what we are going to do is we are going to just look at uh, some some basic type of plastics, some uh, basic manufacturing process, the ones which are very common, and yeah, so that's about it. And also we'll look at some design considerations and some defects and all that happens to it. So those things are quite interesting to see, so I thought I would include that. So without further ado, let's take a look at what the presentation is. Okay. Yeah, good afternoon, everyone. Thank you for joining in. Stay till the end of the class. Okay, we will have an assignment towards the end of the class, so yeah. Okay, so yeah, so I'm sure you know plastics, right? So everybody knows plastics. It's uh, one of the most world-changing materials in many ways than one. Okay, firstly, it is like such a versatile and such an amazingly versatile material that you could make any shapes, and you could design plastics for any kind of application, starting from basic things like designing containers and all that, to highly specialized like engineering applications. Okay, like let's say in aerospace and whatnot. Okay, so any kind of field that you think of, plastics is one of those materials which is used extensively in it. Okay, whereas the problems with plastics, everybody knows this, is they are inherently not biodegradable. At least there are most of the plastics are inherently not biodegradable. In fact, it's slightly difficult to even recycle some of them, because they do not retain the properties that they had initially when you recycle them. So unlike metals, where what happens, let's say aluminum, you could recycle it multiple times. Okay, and it would still remain a certain aluminum. Okay, it will not degrade per se. But because of the nature, the chemistry of plastics, over time, it degrades. Okay, it degrades because of exposure to the elements. It degrades because of multiple processing. Okay, the energy that you kind of impart into it. Okay, so yeah, and we have a major environmental concern because of plastics. We will not go into that domain in this course. We are going to look at it from a positive perspective. We are not going to vilify plastics. We look at it as a very important engineering material, okay, and a material important for design, right? Okay, so yeah, I don't know if you've seen how plastics are made before, but what actually before it becomes anything, right? So generally you get plastics in these kind of beads and pellets. Okay, so what you see over here are different types of beads, right? So these are plastic beads of different types. Okay, and this is recycled plastic or reclaimed plastic. So plastic which has been found, recycled and shredded into these small pieces, and these also you can use to manufacture. Okay, you can already see that there is some kind of discoloration. The brightness that is there over here, it's not that, it's also because of the additives and all that, but uh, you can kind of feel a recycled plastic. You can identify recycled plastic slightly by feel. Okay, not always, but yeah. So anyway, this is the starting point. So uh, from the so the origin for plastics material is petroleum, right? So petroleum is extracted, refined, and there are several different types of things that are made from crude oil, and one of the byproducts is these kind of plastics, right? So polymers chains are created. There are of course many other ways, like for example, the base material could be lactic acid, right, uh, which is typically extracted from cornstarch and some natural materials. So even from plants and all these kind of plants, and I don't know of any examples of, let's say, plastics being extracted from animal items, but yeah, let's say plants. Polylactic acid is something very common to most people, where the plastic is extracted from plant byproducts. Okay, right. So this was a very interesting graph, or an image to show different types of plastics. There are hundreds and hundreds of types of plastics, and too many to cover naturally in a course like this. uh, and even in a very specialized plastic course, I think only like 2% of the different types of plastics are covered, right? And that those two are covered in a very broad sense. Okay, so this chart, this image kind of gives you an idea about what are the different types of plastics and how it is categorized. Okay, so at the bottom, what you have is something called commodity polymers. So these are the polymers which have become commodity. They are largely used in FMCG products and all these kind of fast moving products. Okay, where you make thousands and thousands of pieces. Okay, so things like PS, which is polystyrene, SAN, PVC, polypropylene, HDPE, LDPE, all these kind of plastics are there. So on the left hand side, you see that these are the amorphous types and these are semi-crystalline types. So the difference is that unlike metal, what happens in metal and metal alloys is that the elements kind of arrange themselves in these crystal patterns, right? So BCC, FCC, and all these kind of things. But the chemistry of plastics and the molecular structure of plastics is different, and they can't arrange themselves in these forms perfectly. However, there are some materials like polypropylene and HDPE with display some crystalline behavior. Okay, so those are called semi-crystalline. So they don't necessarily arrange themselves into BCC and FCC structure, but they are somewhat crystalline, is what you can say. Okay, beyond so commodity polymers are the ones that you should really know about in depth. Okay, and beyond commodity polymers, there are engineering polymers which are mostly used in slightly higher grade kind of applications, or slightly upscale applications, or slightly engineering centric, or applications where the property of the material is important. Okay, so for example, polycarbonate is a type of engineering polymer which is used, let's say, in making visors for helmets, the transparent visors. Okay, those are plastic, right? So polycarbonate, it has a very good transparency property. ABS is another type of plastics which is used in many of these high strength kind of products, where the outer casing needs to have slightly higher strength or better finish. And in fact, like for example, let's say car dashboards, if it's made out of plastics, most likely it will be a combination of polycarbonate ABS. Okay, PMMA is acrylic. Okay, so yeah, you all know acrylic. There is some form of polypropylene also, with some modified, additives and all that which are added, which can be used as in many engineering applications. Okay, then you have these high performance polymers which have very specialized applications, let's say in making implants. Okay, so for example, hip implants, no, they have some parts which are made out of plastics, and these are called ultra high molecular weight plastics or something like that. And they have very specific properties suited for those kind of applications. So there are many such high performance polymers also available, but these are not really seen in consumer products as much. Okay, unless there is very specific requirements. Okay, like let's say friction, or corrosion resistance and things like that, if it's required. Okay, and then there's another special type like ultra polymers, which are very very niche kind of polymers in very specific applications of aerospace, and these kind of aerospace plants and refineries, and these kind of basic examples is what I found. I couldn't find a specific example in a product per se of ultra polymers, but anyway, so this is one type of categorization. Okay, and plastic is like an overall term which is used to describe all these kind of polymers and resins, which so the internal structure is mainly consists of elements like hydrogen, carbon, nitrogen, fluorine, silicon, things like this. Okay, and they are typically derived from oil. You could derive it from crude oil, but you could also derive it from some plant byproduct oils. Okay, yeah. So the categorization that most of us are aware of is this. And there are two types of polymers, which is thermoset polymers and thermoplastic polymers. Or there are two types of plastics: thermosets and thermoplastics. Okay, and thermoplastics the is basically the are basically the plastics which melt with applied temperature or heat. When they melt when you apply heat. Okay, they're based so the distinction this distinction is based on how the polymer network, uh, the word polymer network is of importance here, how it responds to heat. Okay, thermoplastics, remember the word plastics and equate it to, let's say, metals. Okay, plastic deformation in metal, what does it mean? Okay, so similarly thermoplastics are the ones which soften and melt when heated, and they harden when they are cooled. And thermosets, what happens is that in thermoplastic, mostly the internal structure are these long chains of polymers. Okay, long chains of different types of elements connected together, and it's like noodles. Okay, and the whole thermoplastic material is this noodles kind of uh, noodles in a bowl. You can imagine that way. Whereas thermosets is there are noodles connecting these two noodles. Okay, so these are called crosslinks. Okay, and there are other forms of crosslinks and interconnections between these long chains of polymers which limit the movement of the chain. In the case of thermoplastics, what happens is that because they are like these large noodles, uh, in a small bowl, you can move it. It's easy to move this kind of a polymer chain. Whereas if it's cross-linked, it becomes much harder to move it. That means if you apply heat and energy, then it's difficult to move these long polymer chains because of such interconnections and cross links. Okay, so yeah, thermoplastics, there are two types in this categorization: commodity and engineering. Engineering are the ones very performance centric, whereas commodity are the ones which are used in most consumer driven applications. Okay, right. So there is so this is basically the categorization. There is a lot of details that you would get to know if you take the plastics and composites course, and that course actually goes in much more details of how these polymer chains are created, what are the different types of polymer chains, and how they are uh, are affected by heat and temperature and all these kind of various things, right? And what is the mechanical behavior and all those kind of things, right? So yeah, so that details remains for the other course. If you are interested in the manufacturing technology book, there is a specific section on plastics, so you can go through that. Okay, so but here we want to know a little bit about some important properties, and one of those very very important properties is what makes plastics a plastic. So there is this property of glass transition temperature. You can see the video down below. The glove is made out of nitrile. It's a type of elastomer, right? And this guy is dipping it in liquid nitrogen, and what happens once he dips it, it almost becomes like it crumbles, right? So it becomes hard and it crumbles. Okay, so this kind of shows you the property of glass transition temperature. Okay, which is typically denoted as Tg, and this glass transition temperature is the temperature at which the material transitions from a glassy, brittle, rigid states to a leathery state. Okay, now depending on the type of material, the room temperature, normal room temperature, may be above or below the glass transition temperature of this material. Now let's say nitrile glove. In the case of a nitrile glove like this, the glass transition temperature is above the or glass transition temperature is below the room temperature. So when he cools it in nitrogen, uh, the material crosses the glass transition temperature and it becomes brittle. Okay, and most uh, plastics which are hard, let's say this piece which is hard, right? So this the room temperature uh, is lower, higher is higher than the glass transition temperature. Am I saying this wrong? Okay, right. The room temperature is lower than the glass transition temperature, so that's why this is harder. Okay, and this property is important because this is what uh, is considered when manufacturing plastics. Okay, so for example, if you want to manipulate plastic, then you would need to heat it to a certain state which makes it softer, right? So if you want to put it through an injection molding machine, you should know what temperature it will start melting, it will start behaving, it will start flowing, right? So, and that all those things are defined by the position of this glass transition point. Okay, so here you have an example of a certain polymer, and the here on the y-axis you have specific volume, on the x-axis you have the temperature, and Tg is the glass transition temperature. At certain after this glass transition temperature, there the polymer chain kind of uh, uh, breaks at certain intervals, okay, and that makes it easier to flow. And yeah, so I'll not explain this too much. I mean, it it has a lot of other details to it also, so I will refer you to the book, and I want you to go and read about it a little more. Okay. Okay, so glass transition temperature is a property specific to, I think, thermoplastics, whereas in thermosets, such behavior is not clearly seen. Okay, this transition from a leathery state to a brittle state is not seen. Okay, and here in thermoplastics there are these kind of common ones that are there. So engineering plastics, let's not consider that, let's talk about the commodity plastics. So all these is are the types of commodity plastics, right? So one type is a polyolefins, where you have something called polyethylene, polyethylene, right? You have low down density and high density polyethylenes. Okay, ultra and high molecular weight polyethylene. So these kind of this material is used, as I said, in implants, let's say. Then polypropylene and all these kind of things. And in vinyls, these kind of ones, the common one is polyvinyl PVC, which is you already know that there are a lot of material, things that are made with PVC that you can find at your home. And finally polystyrenes. So these polyolefins, vinyls and styrenes are the monomers that are there, and once you polymerize them with certain types of additives and all of that, they become these specific materials, plastics, right? So ABS and polystyrenes are in the same family if you consider the monomer. Okay, styrene monomer, right? Okay, yeah. So I'm not going through all of this. So similar categorization, if you want to do thermosets, these are the different types of thermosets, monomers that are available, and the some examples of the plastic themselves, right? So epoxy, I think most of you are familiar with. Okay, there are several hundreds of different types of epoxy compounds, and the way thermoset plastics so in terms of raw material, how it happens is that in thermoplastics you get the final formed polymer in those beads. Okay, and then those beads you can melt, and you can, let's say, I will use the word cast or injection mold into any kind of form that you want, right? In terms of thermosets, however, generally what you get is part A and part B. Okay, in epoxy that's more true than in others, right? So you get two kinds of two parted things, or two things which when you mix together, the polymerization reaction, it happens after mixing of these two in situ or in location, right? So, and that polymerization reaction is such that you create these long chains and you create these cross links also, and that's how it becomes like hard and all that. Okay, right. Okay, so so there are some general recommendations of how and of which types of plastics to use in which scenarios, right? For example, if you have uh, a requirement of making gears, or let's say some fan blades or something, so it's better to go for with something like acetyls, nylons, polycarbonates, and polyamides. Okay, so if the requirement is, let's say, frictional property, so you need low friction. Okay, you need some things to slide against each other. So polyesters, polyamides kind of are better suited for such um, you know applications. So similarly, chemical resistance, if you want to, let's say, store chemicals, okay, you can use some of these types which would not react with the chemical that is being stored. Okay, yeah, so these are like just general recommendations of the applications of different plastics. Okay, there are several types here, so I'll leave this to you. So this is just like a reference image that is there for you. So if you need it sometime, then you can access this and you can see. So let's say I want to create a product which has x and y properties, or a part which has an xy property. You can choose the polymer type that would be suitable for you. Okay, now this is very interesting actually. So how do you identify? So it is sort of possible to identify what plastics do you have. Okay, so let's say if you have a piece of plastic, so this one. Okay, what exactly is this? So first step to do is to look at the bottom of every product. So I want to show you this. So at the bottom of every product, let's see if it focuses. Does it focus? Focus, 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 focus. Wait, 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 wait. Okay. So if you see here, there is like a small triangle here. Okay, I don't know if you can see. So here, the small triangle that's there. Okay, so in every most products, plastic products, or the most well made plastic products, typically you will see these kind of triangles. I think in this bottle also it has. Wait, 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 wait. Where did it go? uh, can you see? I don't know if you can see. So I want yeah, just a second. I got it. Yeah. Okay, can you see that triangle? It's shining just a little bit. So every plastic product has this kind of a triangle underneath. So best way to identify what plastic it is to look at the triangle, and generally it tells you what plastic it is. So this piece that I have, it says there's a 1 inside the triangle, and it says PET, which is like it's PET. Okay, this is a PET bottle. Okay, uh, right, but let's say if you don't have, let's say you just have this piece over here. Okay, this also has the marking, but let's assume that this did not have, then how would you identify? This chart gives you a interesting idea. So first is to, let me transition. So first step is to heat the tip. So I would heat this piece, and I would see what happens. What is the property that is there? Okay, I don't have. Should I? Okay, I'll do this experiment for you. Let me try and do it. Hold on. Right. So I have this broken piece of plastic, right? And what I'll do is, the first step is to heat it. Okay. Right. Turn off the fan. Don't try this at home, or actually you'll have to try this at home, because this is kind of your assignment. Okay, so if I heat it, and what I see is it's softened, it's much softer than before. Okay, so so this tells me that it is thermoplastic. Okay, then the next trick is to drop a small sample in water. Okay, and if it floats, then you know that it is polyolefins, or if it sinks, there are chances that it is all of these other parts. Okay, right. Okay, so let's burn this sample and let's see what happens. Okay, and after that, the flame characteristics is what will tell you what exact plastic it is, or it will get you to the closest to what plastic this is. Okay, okay, it's right, it's dripping, and look at the flame characteristics and all that, and make sure that you don't hurt yourself doing it. So yeah, we saw what happens. Okay, so we didn't do a drop test in water. I don't have water. Do I have water? I have a little bit of water. Let me try it over here only. Okay, yeah, it's floating, right? So most likely it's a polyolefin. Okay, and we burnt a sample, and what we saw is the color of the flame, it's blue with yellow tip, and it was blue with yellow tip, and chances are that it is polyethylene or polypropylene. What was the odor? The odor was uh, so this one says it's paraffin odor, or acrid or diesel fumes. Okay, it was fuming just a little bit. Okay, uh, and finally, now I'm kind of indecisive between polypropylene and polyethylene. Speed of burning, was it fast, was it slow? It was fairly slow. It was not going like वैसा करके नहीं. It was not too fast. Okay, and finally, does it scratch with a fingernail? Okay, so polyethylene is fairly you know uh, uh, softer. Uh, so instead of fingernail, I can also use some other simple metal and see, and it does not scratch easily. It's a little oily, so that means it's olefin, and it does not scratch easily. So most likely it's polypropylene, and I think that's true because this is a piece from a marker, marker cap. Okay, so you need to do this. Okay, so this is what there are. So there are two parts to your assignment. Okay, today. So this one will be one of the part. Okay, so keep this in mind. I'll keep this slide. So naturally, all the slides are available to you. This image is within the slides. It's a little it's a little too big, so you might have to kind of squint your eyes and see what are the things. So yeah, so okay, remember to be safe. I'm assuming that, are you all above 18 years old? I hope you guys are, right? So that means technically you are adults and you don't need adult supervision. But if you are below the age of 18, please ensure that you get some adult supervision. Okay, uh, ask your mom or dad or somebody in your family to help you with this, right? Okay, so this is about right, thumb rule identification of different types of plastics. Okay, let's go forward. And the thing that I told you about the triangles at the bottom of every product, so you can easily get like what kind of material that is by looking at these triangles. If it's one, and it it is either polyethylene or PETE. There are different types of PET which are available, right? So these and this here tells you about some of the properties that are there. So there is some clarity, that means it's transparent. It is a fairly good moisture barrier, and it can resist up to, in American units, 176 degrees, and so on, right? And yeah, so you get this kind of a triangle at the bottom of most products. So this one is wait, this one is also PET. Okay, I am mostly PET plastics over here. Okay, but you get a lot of products which are made out of ABS and all these kind of things. My friend runs a very amazing Instagram page called Material Material Wisdom. Okay, and every year when I have this course, he gains another 15 or 20 followers. Okay, so I don't want to disappoint him this time also. Okay, so go ahead and subscribe to this, it's not sub follow this you know page on Instagram. It's called Material Wisdom, and it tells you about it gives you a lot of details about different material types and all these kind of. So I've got these images with his permission on these slides, and these are all his images. And so this one is a soap case, a kids soap case, and it's made out of ABS. And ABS has amazing impact strength, and it has good resistance to corrosion. So you can see the application using soap and anything that might have oil in it, and so you can use it for all kinds of pipe fittings and plumbings, and you know so if you have a plastic product which needs to have really shiny finish, and it should feel very rigid, and it should feel very nice to hold, then ABS is the right material to go with. It has a very good tactile feel to it. Okay. uh, so this is an example here. For example, ABS, you can make it with this thing also. You can make it transparent also. This is a tool case of Dremel, and it's available in all kinds of things. So this is fairly common in expensive products. Okay, I should put it that way. The other common one is polycarbonate. So this is an example. So the name is Material Wisdom. Go and follow this page. Okay, and polycarbonate is basically it's transparent. So that's the property which kind of sells it. Okay, which because of which people tend to use it in products. Okay, so bike visors, as I said earlier, so it's made out of polycarbonate. It has excellent mechanical strength, almost comparable to ABS, and it's so the problems are, it is affected with oils and grease and acid, and it gradually becomes brittle if it's continuously exposed to let's say sunlight. Okay, you can say sunlight also. So it will gradually lose its properties and become brittle. So when you break polycarbonate, it will have a very uh, glassy break. So that means it will crack. Okay, it will break into pieces. Okay, and it's also used for these kind of properties like EMI, RFI, and ESD shielding. So that means so EMI is electromagnetic interference, radio frequency interference, electrostatic discharge. So these kind of shielding are required when you have some electronic components which are highly sensitive to these stray electromagnetic radiation or electrostatic discharge. Okay, so you can use polycarbonates as materials to shield these components. Okay, PET is the other ones that we saw. So this is PET, right? And it's used for PET bottles, right? So it's used for because it's much easier to manufacture, and the process of manufacturing in which it's made, which is blow molding, it's very compatible with those kind of manufacturing processes. It's durable, it's tough, and yeah, overall these kind of properties. Polypropylenes, I had this bottle myself, and so this part, the colored part that you see, okay, that's silicone rubber. This is glass, and the cap is polypropylene, is what is shown here. A lot of products which are there commonly available, right, it's made out of polypropylene. So we saw here this piece of so so I have these small markers, pens, which are made out of plastics. Most likely it is polypropylene. So polypropylenes have a oily feel to them, slightly slick and oily feel to them, because they are in that oleofin you know category. So yeah, okay. So next, there are so many different types. Okay, what I did was, from the plastics and composites course, I took some of the slides which I thought were interesting and or right relevant and common, and put it in this presentation. So that's how this was designed, right? So cellulosics is another type of plastics which are very very hard, right? So like cellophane paper, and what you use to cover food, right? So those kind of films can be made using some cellulosics material, okay, cellulosics types of plastics. And you can make all these kind of uh, products where, you can think about it. So what is the material property which makes this handle to be made out of this plastic? Okay, it needs to be rigid, it needs to not change over time, it needs to have a weight and heft to it, right? And it should not be slippery, and all those kind of things are there, right? So yeah, and it should interface well with the metal. So these kind of requirements which are suited, so cellulosics are suited for this kind of application. Then nylons and polyamides. Nylons fall in a family of polymers called polyamides, and this so nylons. So for example, in this one, right? So this is a screwdriver, I think. Yeah. So in this screwdriver, this part, the blue part, is made out of nylon. Okay, and you can see there's specific type of nylon which has 30% glass filled nylon. Okay, so this, not just it's not entirely a single type of plastic, it's a composite plastic. So it is made out of nylon with some glass fibers to increase its strength. So you can imagine what makes it suitable for this kind of application. So this product might have a lot of vibrations in its body. So the body needs to withstand these vibrations, okay, and it should withstand it for a very long duration. So there should not be micro cracks that form inside the product. So nylons kind of have these properties. However, there are some problems, like they are hygroscopic in nature. That means over time they'll kind of accumulate water inside them. Okay, so you have to think about those kind of issues. So let's say if you're combining them with metal, they are in contact with metal. Those parts where the nylon material is in contact with metal, you need to be very careful, because chances are there'll be more rust buildup at that interface. Okay, right. Okay, yeah. Okay, then there's another special category which is PCABS alloys. So it's a very loosely defined term. Alloys, it's not really like how metal alloys are there. Here, the bowl of noodles that you, if you consider the plastic material to be the bowl of noodles, there are two types of noodles. Okay, so this is how it's an alloy. Okay, and it's used extensively in this luggage industry, because it's really really strong, and you can mold it really really thin, and you get that same kind of structural rigidity in those, and it has high gloss and high finishes, which makes it suitable for such applications. Okay, Silicone is one which you will see commonly. So what you see here is a silicone material. I'm sorry, there's someone at the door. Just give me a second. Sorry about that. Okay, yeah. Then there is this one also, like, which is TPU. You'll see this. It's a type of polyurethane, and its name is thermoplastic polyurethane, right? So you'll see this very commonly also. And polyurethanes also used a lot in insulating, buildings, right? So you see this, it is polyurethane foam. So some additives and some additional things are added, and when it is sprayed, this thing kind of foams up and it becomes this hard foam. Basically, you have this in the we have this in the department. Sometimes students use it to make models. Okay, so here you see it as foam, but it has already hardened. And yeah, I mean, I can't really describe the property properly here, as in what it feels like, but it's not exactly like thermocol, where thermocol is much softer. This is much harder, and when you sand it, uh, it gets sanded well. Okay, so it's really good for form explorations and all also. Anyway, so yeah, that was like a very you know crash course of all the uh, plastics, some of the plastics materials. So let's take a look at the manufacturing side of things. So how would you manufacture plastics? The most common one that we know is injection molding, right? So and I told you, actually, we were going to discuss just injection molding, but I thought, okay, some context would be really good. So let's take a look at this small animation. In this presentation, by the way, there is another video that I'm not going to show here on YouTube because the video will get some copyright strikes and all. But what you can do is, the once the presentation is available to you, you can go and see that video. That has a much better explanation or much detailed explanation of what goes on in an injection molding machine and why it is so interesting. Okay. So here, so let's take a look at this video. And so this is what we want to make. We want to make a plastic part which is like this. Okay, you have these bosses which are coming out, and this is what the machine looks like. A stripped down version. Basically, we've removed all the other parts that are needed in the whole machine. Okay, we've just stripped it down to two major components. Okay, one is the tool itself, and the part that holds the tool. Okay, let's call it that way. We are not going to look at the jargon of the whole thing, but we just want to understand how this thing happens. Okay, how injection molding happens. So this is the die. Okay, these two pieces are the die, and as you can see, unlike, let's say gravity die casting or die casting aluminum dies, this is much more complicated. You can see these kind of fittings that are there. Okay, so these fittings are there basically to cool the die. So behind these fittings, what die makers have done is that they have drilled channels internally, and they've drilled it in such a way that you can pass fluid from one end, and the cooling fluid will come out the other end, and it will run through in a specific pattern throughout the die, and it will cool down the die to a certain temperature. The reason you want to do that is because uh, you are handling hot plastic, right? And over time, and the cycle time of making a piece of plastic is incredible, actually. So such a piece, for example, what is shown over here, this probably will be made in half a second. Okay, so in half a second, the material is molten material is shot into this cavity. This thing opens up, and you can remove the whole piece. Okay, so it's that fast. So you can imagine using it over time. There is some impact of the temperature gradient that will happen on the die itself. So because of which this kind of cooling and is required, and this is also to ensure that there is uniform, temperature. The heat is uniformly distributed around the die itself. It's not hotter in a certain zone and colder in others. Okay, so that's the reason that you have these things. Okay, so let's move on. And so you can see there are these pins that are there, and there are springs over here. Okay, and this is, by the way, the whole machine. This is how it looks like. Okay, there are a lot of other subsidiary or auxiliary components which kind of help the whole injection molding process. Naturally, there is a console to monitor the whole thing, but this one is where the plastic kind of comes from. So this is like a hopper. That means the pellets that I showed you in the starting of this lecture, those pellets are over here. Okay, and they are fed into this kind of a tube, and in this tube there is a screw which has a certain specific design. Okay, so the screw, once the screw rotates, it kind of pushes those pellets forward, and these black pieces that you see over here, these are heaters, and they heat the outer casing where the screw is held, and internally, because of this heat, the plastic, as it travels through the screw, it gets molten. Okay, so yeah, and so those plastic pieces are put in over here, and these are the heating elements, and that's the screw that I was talking to you about. And there is, I don't know if you are noticing, but you can see the screw is not of uniform cross section throughout. Okay, it has a, a smaller diameter. The shaft of the screw is smaller over here. As it goes forward, it gradually increases, and to a point where from where it remains constant, right? So you can imagine what happens to these pellets that are pushed forward by this screw. Okay, they get squeezed to a certain and they get squeezed as they travel through the screw. Okay, let's take a look at this if it shows that. Okay, so this is the feed zone, this is the transition zone, and that is the metering zone. Okay, so the reason there are three zones is, here the feed zone is fairly straightforward. That means the material is pushed from one end to the other at a certain constant rate. Okay, during the transition zone is the part where the plastic is actually melted. Okay, and in the metering zone you decide how much material is required to be pushed into the mold cavity. Okay, and yeah, let's see if it so it gets pushed in, it gets melted, and it comes forward. So now once it comes forward, this is like it acts like a non-return valve. So this thing, so the molten material cannot come forward. Okay, so yeah, once this is showing you like the cross section, you can see that these are the holes which are drilled through which these coolants kind of pass, and these coolants ensure that the mold is at a uniform temperature. Or the other thing that it ensures is that when the plastic part cools down, the cooling happens at a uniform rate throughout the part. Okay, it's not like it cools at a certain location more than the other, which may induce some problems of warpage. Warpage is like uh, so I want this plastic to be straight, but what I get is something like bent like this. Okay, that is warpage. Okay, let's take a look at what happens. Now the whole screw kind of pushes forward. Okay, and it injects the molten material into the cavity. Once that happens, this thing cools down and this retracts. Okay, once it retracts, okay, I wanted to show you this. So it retracts. So pay attention to what happens to these small pieces over here. Okay. So the backing plate, so this small plate over here only moves to a certain distance. Okay. And whereas this die piece keeps on moving back. So these pins are pushed forward. Okay. And once this pins are pushed forward, because of that the plastic part, the part itself is ejected. Okay. So these things are called ejector pins. So we can see it again. It cools down. This thing moves back and the part is ejected. Okay. So these things are ejector pins, and if you see closely in most of the plastic parts, I will not be able to show it in video because it's very tiny. You will be able to see these ejector pin marks. So they are generally circular in nature, but sometimes you may have like different shapes. Okay. Right. So this is basically the injection molding process. And some terminologies from casting kind of get taken over here also. So this is the gate. So this molten material where it travels, that is the sprue. There is a gate where the sprue touches the part itself. All those considerations of mold front, or sorry, flow front, and the temperature considerations, those becomes important for injection molding also. Okay. And the part is ejected. Okay. I think it repeats one more time. So that is how the injection molding machine looks like. Okay. The design of the die is something very critical, and that is what is the expertise of most of these mold makers. uh, uh, they'll have a specific type of a machine and they'll design the die which can work in that machine, and the die will be designed in a manner where these cooling things are taken care of, and even if you have some types of undercuts, some simple undercuts, those features can be dealt with. Okay. Okay, so this is injection molding. There are some basic guidelines, of course, like the draft angles is something naturally very, very important. So draft angles should be at least 0.5, but 0.5 is just a little too little, is in my experience. It's a good idea to go up to 1.5. 1 degree to 1.5 degrees is a good draft angle, is a safe draft angle. But yeah, in some situations you can kind of reduce it to 0.5. Okay. The injected plastic will follow the path of least resistance. So naturally this is a fluid when it is injected, and it is injected at a certain pressure, right? So you can see over here how the flow of the fluid happens. And so this chart here gives you the time. So you can see this whole part, I don't know how big it is. Oh, this is around 6 inches wide, right? So it takes around 1.6 seconds for it to go till the end, okay, which is here. Okay, and this is the gate location. Okay, and this is where it is going to be injected. Okay. In plastics, it's good idea to keep the part wall thicknesses uniform, or at least within 10% difference. Okay, so that means if one part is of thickness T, then the joining parts should not be more than 1.1 D. Okay, so that's like the thumb rule. So these are just thumb rules. Okay. So yeah, well, naturally you saw it's a very critical kind of a manufacturing process, and it's there's like extensive knowledge on this. Okay, this is probably one of the manufacturing process which has more knowledge base than all others. Uh, uh, yeah. So, but still, you'll always end up with some kind of defects, and there should be ways for you to identify these defects. Okay. So these defects, so what happens in plastic manufacturing is that once you have the design ready, you give it to a mold manufacturer. The person, he redesigns the part sometimes to make it suitable for injection molding. Then the injection mold itself is designed once the whole thing is approved. And once the mold is designed, you start making some initial pieces. Once you make these pieces, you find out some problems that you see there, and you modify the mold accordingly. Okay, so it is a design process in itself. The mold design, it's a design process in itself. You find out the requirements from the customers, you underline what are the requirements that you need to take care of, then you design the mold, then you prototype the mold sometimes with softer metals, and then once it gives you the kind of solutions that you want, the plastic parts that you want, you take it to the actual manufacturing of the mold, test it. If there are some errors, then you rectify the errors and make the final mold, deliver the final mold. Okay, so that's a design process in itself, right? And the kind of problems that people look for are these. So these are the common failures in plastic parts. Okay, and most often than not, you will see them in some of the parts that you already have with you. Okay, so so I'm giving you examples of each type, so visual examples of each type. So first one is splay. So splay is where you see these kind of lines in the plastic, and it's typically like radiating outwards of the uh, gate, okay, where the material was injected, and it generally occurs when material is hygroscopic and it's not been dried properly. Okay, so when in so based on that, some parameter in the machine is tweaked. Okay, then flow lines. This also is fairly common to see, and flow lines are caused because of the variation in speed in which molten plastic flows when going around the geometry. So let's say here, so you can clearly see that these are flow lines, and from the way the flow lines are there, I can estimate that the gate is somewhere over here or somewhere in the middle. Okay, somewhere over here. So basically the material flowed like this, it came around these parts and it flowed. And the reason you get these flow lines is, so it's especially more evident if there's some kind of surface additives in the material. So if you need some shiny plastics or particles in the material, in the plastic part, then if you add that, then they'll result in these kind of flow lines. Okay, weld lines is similar to misruns, right? So here you can see these two weld lines, okay, in a plastic part. So let's say, so what happened was probably, okay, yeah, so let's say the gate was over here. So you pushed material from over here, the material flowed from this side, or I think the material was pushed from over here. The material flowed this way and this way, and the flow fronts kind of joined together at these points. Okay, and the material got welded, and this kind of small surface defect was created. Okay, so to rectify this, some flow parameters are tweaked in the machine, how fast you fill and all those kind of things. Okay, flash is fairly common. You can see this in a lot of cheaper plastics, where if the molds are old, they don't close together properly, and there's a gap which is created. So you can see these gaps over here, okay, in the mold. So it caused a flash, right? Then there's some jetting. So this is similar to flow lines, but so what happens is that uh, once you put the material, once you push the material, it kind of behaves like a toothpaste. Okay, in the first few moments of the whole injection. So that it helps in the overall filling of the part, but that kind of um, stream, it remains in the final part. So that's the jetting. So the material was able to flow, if you see these kind of jettings, the material was able to flow, but that initial part was the problem. Okay, so yeah, sink marks are the ones which are more common than all of these others, and you can see it on almost all of the in most of the parts. Okay, you won't be able to see it in Apple plastics or and all that, but you will be able to see it in all kinds of plastic parts, almost all kinds of plastic parts. So sink marks are basically, if there are thicker sections up, sink marks result from shrinkage in the thicker sections of a mold. So by looking at this portion, I can say that this part is thicker. Okay, and what has happened is that, so since the mold part is thicker, mold at that point is thicker, so once it cools down, one of the surfaces kind of caves in, the material shrinks and kind of caves in. Okay, and this kind of gives you such a surface defect. Sometimes it might be acceptable for you to say, if you're making some parts which do not rely so heavily on visual aesthetics and all that, you can say it's okay. Or sometimes you can specifically ask the mold manufacturer to design without any sink marks. Okay, so in which case a lot of design iterations may have to be done. Vacuum void is if there is an inclusion of a bubble or something like that in the mold. Okay, or rather a cavity in the mold. Okay, so vacuum voids are bubbles within a part that can weaken its integrity. They result from trapped air or differential shrinking. So at this point, maybe it shrunk in all these directions. So this is similar to, let's say, a casting defect that we looked earlier. Shorts are, let's say, if you wanted to make this kind of plastic part, which is, it needed to be fully closed, you did not push in enough material, so that this is what happens. So this is a short. So that means that injection short, you did not put enough material. Okay, and warping, as I said, it's a it's again a very common kind of defect that you see, and the reason is that the overall cooling down of the part. Okay, so you can see this is a warped part. It did not cool evenly, and that resulted in this kind of a warpage. Okay, sorry. Burn marks. Sometimes if you have these kind of blind pockets, that means at the end where the flow front meets and closes, you may have to heat the material to a very close temperature to its burning point to ensure that the flow remains sufficiently viscous that it fills up the whole mold. Okay, so if you're flirting with that kind of a temperature, then you end up with something like burn marks, where the material was heated to a much larger temperature and it got burnt. Okay, and yeah, this is surface delamination. It is a very typical failure of in plastics. You get these kind of problems where the surface is kind of comes out in layers. This is because of the settlement of the polymers in polymer chains along the surface line. So there's there's a much higher friction between the surface and the surface of the mold and the polymer chains, right? So they kind of tend to align themselves along the surface, but consider a layer just just beyond it. It need not be so much aligned, so there's like this layering effect which happens. Okay, and these layers can end up with a defect. It's a fairly uncommon defect. Okay, okay, yeah. Draft angle, we will not discuss this. Let's not discuss this. You already know the slide is there here, and there's some details over here that needs to be that you can think of. Okay, let me just take a look at. Okay. Okay. So in terms of plastic manufacturing, draft angles are typically added at the cavity side of the tool. So that means, so this is the core and this is the cavity. Um, the parts of the die where you have machined in, okay, that is the cavity, and the part which is machined out, or that is the core. Okay, and typically draft angle is added in the cavity side. Okay, this shows a draft angle of half a degree. It says minimum half a degree. And the reason you add a draft angle are two things. One is, of course, once you open the mold, you should be able to remove the whole piece easily. The other reason is that, uh, between the cavity and, let's say, the plastic part itself, it the there's no gap between these two when the plastic is solidified, right? So if you try to pull the plastic part out, no, it will not let you, because there's no place from where air can pass into this place, okay, into this cavity. So it will work like a vacuum suction cup, no? So it will work like that. So this draft angle actually allows for a much easier withdrawal from the mold by letting air in also. Okay. uh okay, so it shows you some example of how you can get parts out with zero draft angles if you need it. Sometimes you do need it. So here you need, in such a case, you need a mold where two or three pieces can break away. Okay, and it's possible to design such a mold. Okay, and if you add like textures to your part surfaces, then it's suggested that you increase the draft angles naturally to accommodate for these textures. Okay, right. The second thing to take care of in plastic part design are undercuts. Okay, so these small pieces are used to join plastic part. They are called snap fits. Okay, and the design of the snap fit is not in scope of this course, but there are several different types of snap fits, and almost all types of snap fits have to consider the undercut problem. Okay, so here, for example, this surface over here, this small surface over here, this is an undercut, right? So imagine the mold is moving up and down like this. So there's no way I can kind of remove the mold if this is there. So to accommodate this, I can do like a simple thing. I can cut out this. So there is access to this surface from this hole, from, let's say, in this case, the cavity side. Similarly, like features like these and all, cuts like these are added to accommodate these undercuts. So let's say you have a part where you have two holes on the side. So this gives you an idea of how you can get that. So you can design the core and the cavity in such a way, and the gap itself in such a way, that the core and the cavity meet along like the diagonal of the gap. Okay, and that way you can make these kind of openings, and you'll get a small parting line along the opening at the corner. Okay, you see this one? Yeah. Sometimes the best way to remove a piece is to just force it, right? So here in this plastic part, the white part, you have these small notches which acts as latch, which may probably act as latches in some other piece, right? So the best way, instead of designing some elaborate mechanisms, the best way is to push it hard enough that it expands and pops out, right? I don't think you can see part of the presentation, so let me move myself to the right. Okay, so in situations where it is difficult for a part to pull from the cavity, undercut, sometimes the the sliding of the core itself is used to open the tool. Okay, okay, right. uh, and if you have some very elaborate undercut, sometimes it is some specialized manufacturing processes are also possible where you can melt away, so you can make a core, you can injection mold on top of the core, and you can melt away using either heat or chemical compounds to to have a non-traditional undercut design. So this part wouldn't have been possible otherwise. So you would make this piece in a certain type of metal. Okay, you would injection mold on top of this, and then you would melt away this part. So that's the idea in some of the manufacturing process. Okay, so it's called fusible core molding, by the way, lost core molding. Okay, so it exists, but it's naturally, you can imagine this part is now so much costly, because every time you have to make this part, you also have to make this kind of a machine, uh, casted machine piece, and that makes the cost of this part that much more expensive. But considering, let's say, if this part is need to be used in a high performance automobile, this cost is justified, so you can go for such manufacturing process. Okay, so now we can take a look at this kind of some ingenious mold designs where undercuts are accommodated in the part. Okay, so these are small gifs or gifs which kind of shows you how it's executed. So like for example, in this part there is this small notch over here which becomes an undercut. So that notch is accommodated in the ejector pin setup. Okay, so this part moves back, and this is also part of that ejector pin setup. Okay, and you get this kind of uh, undercut. Okay, let me move myself to the other side. Okay, so here's two more. Uh, Sometimes what happens is that you have this kind of a part design which is quite difficult to remove from the core, uh, because not just because of the draft angles, but because of you not being able to let in air and all that. So you have these ejector pin setups where you know it's kind of pushed away from the mold in a different manner. So all of these assemblies and ways of doing it are accommodated in the mold design itself. So you can imagine sometimes it may become very complicated. So bottle caps, for examples, can be made with something like this. Here there is this rack and pinion arrangement. So this, imagine this like a uncoiled gear, right? And these are small gear tooths, and once the mold is removed, you have like a air or a hydraulic cylinder which pushes this rack, and they kind of unscrew the caps, and you get that undercut of those threads in the piece itself. Okay, so it's quite interesting how it's done. So all of these bottle caps, they are made, most of these bottle caps I should say, are made using this method. Similarly, if you need like threads on the outer side, that's more common. See, you see these two rods, they are called cam rods, and look at how they work. So once the die is kind of pushed in, the rod engages, and they kind of pull these two green pieces or dirty green pieces together, and they form the cavity of the mold. Okay, so that's quite interesting. The same idea is shown over here. So this is a core blade, or yeah, so you can see here it moves up, and you get this kind of undercut is possible. Okay, so mold designers are ingenious people, and so these cam rods, you can see it functioning over here. Okay, it's very difficult to entirely understand from the whole thing. So these are the cam rods, and they kind of engage, let's say, in these holes. So this one probably is going to engage in this hole over here. Okay, and when it engages, it kind of pulls the whole mold down, and you get these parts where you have undercuts on the surface. Okay, it's possible to do that. So you see, so yeah, so those rods kind of pull the whole part in together. Yeah. Okay. So we'll discuss two more manufacturing processes, and then we'll close this. Two more common ones, and the first common one is blow molding. So most bottles are made using blow molding. Most likely, this one is also made using injection blow molding. So injection blow molding is a combination of these two processes, and it's a highly automized process where you have a central place, where an injection molding is connected at one end and a blow molding is connected at the other end. So this injection molding machine injects the plastic to certain pieces, okay, preforms. These are called preforms, and then the mold is opened and these preforms are taken to another mold, and you see these tubes, right? So these tubes kind of push air through the whole piece, and that kind of blows the whole thing like a balloon and to the shape of this blow molding mold. Okay, and in the third stage, the it's stripped and it's removed. Okay, so that's the idea. So it's called an injection blow molding process, and this is from this book called uh, Manufacturing Processes for Industrial Designers. Okay, it's a and what was his name? Rob Thompson book. Okay, so yeah. So the other one is rotomolding. Rotomolding is again a fun, low-cost manufacturing process, but it's fairly limited in terms of what kind of features can be created in that. So this toy, for example, was created using rotomolding, and the way it was done is, you have these large molds, and in that you put a certain amount of plastic, which that is enough to coat the whole surface of the mold, and then you heat it and then you rotate it at a very high speed. So you can see the rotations here. It rotates like this and it rotates like this also, and once it's done, it's taken to a cooling chamber where the whole mold is cooled and it's extracted. So this is rotomolding setup. So we can see a small video of rotomolding, and this is the kind of molds that are there. It's very large. So okay, just a second, I'll reduce the video. I don't think it's needed for the audio more, right? And what happens is, yeah, so this is the mold. You can imagine how large it is, and they put in the necessary plastic in this, and they're going to spin it. Okay, and they're going to heat it and spin it. Okay, so you can see these different stations. So you can see this is the setup that they have, this company has, and you can see this one station where it is heating and this one station where it is cooling, and probably the third station is where it is the whatever part they are making is going to be extracted. Okay, all these traffic cones, syntax water tanks, many of the playground equipments, they are made using rotomolding. Okay, lot of fun, right? So now that this is done, this piece is extracted. Some of these high performance briefcases and all that are made using this also. So what they are doing over here is they are taking a router to the whole part and removing the flashes that are created. Okay, and then these kind of fasteners are put in, and they make these really awesome you know containers to transport, I don't know what, right? So this is rotomolding. Okay, then you have compression molding. Compression molding is just like squeeze casting, you have a material which is pressed between between two dies, and the material takes the shape of the cavity. Okay, and these remote control buttons which are rubber kind, so they are typically they used to be made using this. There are lots of other processes now, but yeah, so these kinds that you can easily identify, they are made using compression molding. Okay, and a lot of rubber parts are made using this. uh, you can also make compression molding for some of these high performance polymers. Some polymers like bakelite also you can compression mold, and you can the best part of compression molding is that you can add these kind of metal inserts to the whole part. You can do it in injection molding also, but you can add this and you get these kind of pieces, right? Okay, and finally there is extrusion. I don't have a video of extrusion, but yeah, you can extrude plastic also, and you can kind of make different types of products out of it. So this is about it. Okay, I don't know how many of you are here. Let's see. Okay, so if you are here, just say yes, and we will explain the assignment. Okay, right. So the assignment for today is, let me get to that slide. So the assignment is twofold. Okay, so you have to find three five different types of small pieces of plastic which you can't identify very easily. Okay, what type they are. Okay, not by the triangles. It's very easy to identify the triangles. Okay, or you can do one thing. So take five different types of plastic products. Okay, the ones that probably you can throw away. It's okay for you to throw it away. Okay, because you'll do some destructive testing. Okay, so the first thing, number one, is identify one type using this triangle. Okay, and tell me what this is. So take a picture. Okay, this is the part. So you saw this guy from Material Wisdom, how nicely he took pictures, right? So this is good pictures. So you take good pictures like this. You tell me this is the triangle that I see over here, and that makes it HDPE. It says this is polypropylene. Okay, so you can put in the presentation the photograph, or put a bigger scale photograph. Just give some basic information like this triangle, it says PTFE. The reason, and the next point is, why do you think this plastic was used for this particular application, so for the product that you use? So at least one out of five, at least one you should identify like that. The others, okay, you follow this chart and identify the different plastics. Okay, so you can show pictures, number one. So you show a picture of what you are trying to identify, and you can show either a GIF or a sequence of photographs to tell me, okay, that you conducted this. Okay, and these are the relevant points. So you can see, you first you'll show me like a picture where you dropped it in water. Okay, and you will say, okay, it is a polyolefin. Then what you will do is you will burn a sample. So you will take the picture of it burning, the flame itself. Okay, and based on that you will deduce this. Naturally you will not be able to show odor, but yeah, so you can deduce this and tell me what it is, what material this is, and yeah, that's it. So four of them, just that. So identify four different plastics using this chart, and identify one different plastic using this triangle. Okay, and tell me why that material was used for this particular application. Okay, right. So actually, what I had in mind was also to include this along with that, right? Uh, Along with this assignment. So what I'll do is, so so find examples from your own house of at least three of these problems. Okay, these injection molding defects. Find three different plastic parts with, or you can find a single plastic part. Find three of these defects in one or more plastic parts that you have at your home, not downloaded images, not like what I have done. Okay, so I have just downloaded these images, but you are supposed to make original images. So find one or more plastic parts which shows at least three of the any of these defects. Okay, so you can have flash and all that. Okay, so did you understand the assignment? There are two parts to it. One is the identification of the plastic itself. The second is the identification of the defects. And all of these information you can put it in a presentation in nice flow, and so that everybody can see and understand. Okay, I hope you understood it. Okay, so just tell me a yes or a no if you understood or not. So what I will do is, so just give me a second. So what I will do is, I will write down over here. Or I should. Okay. That's part one. Part two. Okay. I hope you understand. What if we found out that multiple samples are made of the same kind of plastic after doing testing? Okay. Yes. This is a good question. Chances are it is going to be polypropylene a lot. Okay. So what I want you to do is use identify the different material based on fields. Okay. So some uh, try to ensure that you have different types of plastics, four different types of plastic, or at least three different types of plastics. I'm sure you will find three different types of plastics. Okay, but if they are all different, that will be very nice. Okay, So if you do a test and you find that this is also propylene, that previous one was also polypropylene, then find something else, okay, which is a slightly different feel to it. So here you are going to kind of get a sensitivity towards how exactly that particular material feels like, okay, in this exploration. So doing four is what you will have to submit, right? To get or five different types of plastic parts, you may need to do 8 or 10, okay, and it's a very simple exercise. So yeah, so that should be easy, okay. Okay, yeah, so that's the assignment. Easy enough. Can we different plastic bags? Aniruddha asked, can we use using different types of plastic bags? Most plastic bags are going to be polyethylene. I think one of them you can use polyethylene, but if you just try different types of plastic bags, I don't know if you are going to end up with two or three different types of plastic. But yeah, maybe you can try at least one with a plastic bag. That's okay. Try to be unique amongst your classmates, okay. Try to ensure that you are doing something that most people um, may not do, okay. Try to stand out in this, okay. Okay, yeah, so that's about it. And I hope this was informative for you, and it was a very basic of plastics manufacturing. There are so many other things that need that that have to be discussed in plastics. And if you are interested, then I would suggest you to take the plastics and composite course in the next or the next whenever it's available to you. Okay, right. So with that, if you have any questions, I can answer, or we will close the class. Thank you so much for being with the stream for this long. Thank you so much, and I will see you again tomorrow. So tomorrow we will have our final discussion, and we will also discuss about what we will do about the second test. Okay. So yeah, so I'll see you guys tomorrow in the same way. If you have any questions, you can ask. Okay, I'll answer you in the chat even after I'm done. Okay, okay, thank you so much. Can you hear me? Submission date. Submission date for this will be on 28th. Okay, both the assignments which we will discuss today and tomorrow will last date for submission is 30th of November. That's it. Okay. Okay. Thank you so much. Thank you.